Okay. Hey, everybody. Thank you so much for taking time out of your day to be here. And thanks, Jesse, for that introduction. As you've probably pieced together by now, we're going to be talking about adding hysteresis models to the Radia magnetostatics library. So first, just a quick outline of what we're going to discuss today. We're going to start with some background and motivation for why we would care about adding this kind of functionality to an existing piece of software. What ferromagnetism is and how it leads to this dynamic that we call hysteresis. We'll then talk about a couple of the available models for describing magnetic hysteresis before jumping into our first demo of the hysteresis models we've implemented in rsradia. Then we'll talk about a bit of an applied use of hysteresis modeling, which is degaussing, and we'll go right into our second demo, which is simulated magnet degaussing. And then we'll close out with just a pretty brief description of how these things have been implemented so far and some of the future developments that we're planning on making. Keep in mind, we'll have a Q&A session at the end, so please do put your questions into the question box at the bottom of your screen if you have them throughout the talk, and we will get to them at the end. Okay, so first off, why do we care so much about hysteresis dynamics? If you'll remember from your undergraduate physics that in general, magnetization in a material varies in response to an applied magnetic field. So this M, this quantity M, is really a function of H. This relationship is mostly weak or at least linear in diamagnetic and paramagnetic materials. But in ferromagnets, which are pretty common to magnet design, this M of H relationship is not linear. It's not one-to-one, and it's not even necessarily isotropic, so equal in all directions. Basically, in this case, your magnetization depends on the history of magnetization in the material, and that's the dynamic that we refer to as hysteresis. And in the next section, we'll talk about why, sort of, and how that happens. But this is important because then reproducing fields with a particular magnet or predicting the response of a magnetic material to an applied field certainly requires that we account for this hysteretic information. And the reason for this, of course, is that magnetization plays a direct role in field production. The ultimate magnetic flux density B here is just a linear combination of contributions from magnetization and free current fields. And of course, this is why we use ferromagnets in high field applications, because a relatively small H will produce a relatively large M to where you start dominating your magnetic behavior with this first term. So of course, from all of this, we can see hysteresis is certainly a useful thing to know about. But why? Why do we care about adding this into specifically the Radia library? The reason for this is that capturing this kind of hysteretic information, it requires an acknowledgement of some time-dependent dynamics of changing currents, because that is what's going to change your applied field, and that's what's going to change your magnetization. And Radia is, by its nature, a magnetostatics library, where it solves for fields and properties and things like that at a constant current. There are some built-in functionalities to scale the current. That gets a little dicey when you start moving to or through zero current, and you also you would then have to resolve at every step. So it's possible to create a model of your own and to try to add it into Radia, but it would not be pleasant. And then the other issue is that to actually do the field solver in Radia, you require predefined values, sort of field magnetization values, defined in pairs that are one-to-one. So it can't quite capture that true hysteretic dynamic. So what is actually at the microscopic scale? What is really the nanoscopic scale? What is the source of all of this behavior? And originally, this concept of ferromagnetism comes from interactions between the magnetic dipole moments at the subatomic scale. So magnetic dipole moments within atoms. And those are, of course, generally due to electrons, particularly the spins of unpaired valence electrons which interact. This is also why most of the ferromagnetic materials that we see are metals. They have quite a few free unpaired valence electrons. You also get a contribution just from the quantum orbital angular momentum of the electron orbiting the nucleus. It's a smaller contribution, but in some materials it can be significant. And so what you end up having in these ferromagnetic materials is that these magnetic dipole moments interact quite strongly. And within spatial regions, they couple quite strongly. And so within one spatial region, all of these magnetic moments tend to align. Now, you might say then, well, why doesn't an entire material just spontaneously magnetize all the time if it's ferromagnetic? And the answer to that is that what we're really dealing with here is a balance of energy. So the full alignment of all of these magnetic dipole moments creates fields, of course, and energy is stored in fields. And so it costs energy to be a producer of a field like this. And so you're really fighting back and forth between this issue of it's energetically favorable. There's less of a torque on a magnetic moment if it's aligned with all of the surrounding magnetic moments. But at the same time, you have to store energy in the fields produced by aligned magnetic moments. So you end up with this balancing act where you end up getting the formation of stable domains in which the magnetic moments are aligned, but between domains, this alignment does not occur unless you start applying magnetic fields to the material. And so what happens in that case is that any of this energy required to align the magnetic moments in these atoms comes from the external magnetic field. But when you then remove that magnetic field, you're already aligned. And so it's not going to cost any extra energy to align further. You do have thermal effects. So as you remove this applied magnetic field, that just the energy coming from available from the thermal energy of the material will allow some of these magnetic domains to stop aligning, to flip their alignment. But you end up with some amount of remnant magnetization, which is a pretty important quantity when we're discussing hysteresis. So even when we're not actively applying a field, we have some sort of field produced by this remnant magnetization. And as we'll see, that can be a pretty important effect. So let's talk really briefly about some of the models that are available to us to describe this kind of behavior. The first one that you'll hear a lot, especially in undergraduate courses on electricity and magnetism, is the Ising model, which is a bit of a toy model. You wouldn't really be able to use it to model directly real materials, but it does sort of capture some of the qualitative behavior of ferromagnetic materials. And you can see by this video sort of this formation and alignment of domains in a very cold material, very cold ferromagnetic material. So it's fun for a toy problem, but not exactly for real modeling jobs. On the other hand, we have these two other models, the Giles-Atherton and the Prysock model, which are a little bit more descriptive, physically descriptive. And the Giles-Atherton model is actually derived from physical principles, so it's analytical in nature, meaning it is mechanistic. That also means that it's relatively easy to fit to experimental data. And there's actually been quite a few methods published on how to get Giles-Atherton parameters from experimental data. It's also quite fast, and we'll see why when we go into our demo. But the downside is it is restricted to what you would call nominal or normal hysteretic dynamics, which is to say, if any of the assumptions that lead to the derivation of these analytical frameworks aren't met in your material, you may not be able to reproduce the hysteresis behavior using a Giles-Atherton model. But for most standard magnetic materials, it should be quite sufficient. And then there's the Prysock model, which is not analytical at all. It's actually phenomenological, and it's based on this type of object that we invent called a relay hysteron, which actually represent the magnetic behavior in the material phenomenologically. And the upside of this is it's extremely robust. It's broadly applicable. It's used often to describe hysteresis in non-magnetic systems, so things like water systems and other places where you have history affecting the propagation of your dynamics. But it is a bit more memory intensive because, as we'll see, it's basically based on this description of the magnetic material using grid methods, which you end up doing computations over these 2D grids, and it's a bit more expensive. It's also a good deal harder to determine the parameters, and we'll see what those parameters are and why that might make it a bit tough to come up with a nice Prysock model for your magnetic material. But we've implemented both of them, and now we're going to see a little bit about how you can use them in the rsradia library. So this is the link to the repo, the GitHub repo, where we have this notebook stored. If you have a Cerepo account. This should run in Cerepo. I'm just going to be running it from one of our Jupyter servers here. There is this line at the very top, the first cell, which is just all of your import statements. There's a line that will install rsradia for you. Mileage may vary depending on what kind of a system you're using. This should work. If you uncomment it, it should install. Again, the best case scenario would be using this on one of the Jupyter servers where we know it works. So what we can do, let me reset this while we run through so we can see it run live. So we'll run our imports. So the very first thing we're going to do is create just a simple block magnet. So what we've done is, actually, I apologize, I'm beginning on the wrong demo here. So what we actually want to do is run the Hysteresis demo notebook. And so the first couple of cells here are just text. They give you a little bit of information about the parameters that you need to construct one of these models. I'm not going to go into too much detail there. We also offer a couple of options for integrators. So the crux of this Giles-Atherton model is that you're integrating directly integrating equation, a differential equation, not an equation in motion, just a regular differential equation. And we give a couple of options for which integrator you can use. So if you are looking for speed, Euler is quite fast. If you have really nonlinear hysteresis curves and you're worried about stability of the solution, you can use one of our Runge-Kutta integrators. But basically, you just define all of these physical parameters and then the integrator, and also just a step size to use as you're ramping up through different field values. And with just that, we can construct our Giles-Atherton model. You'll see it runs very quickly. Just constructing it already, we've computed the major hysteresis loop and the remanence and coercivity. So that's just part of the model immediately when you've constructed it. But we can also then use these models to compute hysteresis information in a variety of situations. So a couple of the things, what we're going to do here is we're going to compute a minor loop. And we're going to do that by starting from an unmagnetized state, but we're not going to go to saturation magnetization. We're going to go to 1/5 of that. And then we're going to do a minor loop at 1/5 saturation. You can also do partial loops. So if you know a point on your major loop that you're starting, you can start at that point and trace the loop for some user-defined amount of field. And you can also do things like picking a point, a particular applied field, and whether you're on the upper curve, lower curve, or initial curve, we can interpolate the main loop and get back a value of the magnetization at that particular point. And then we can also use one of those points that we've interpolated as a starting point for that loop tracing method. So it's quite should be pretty complete for whatever situations you want to emulate with these models. I'm going to do a plot here so we can see sort of what I'm really talking about here, what it looks like when we do any of these things. So here's our hysteresis loop. If we look at the blue curve, that's the major loop that was computed the moment that we defined our model. And we also have our remanent field and our coercivity. This gold dashed line is where we've said start at the saturation point and move down to 0. The green dotted line is just the minor loop. So you can see we only come up to 1/5 of the total maximum magnetizing field before we start looping back around. And you can do that with any level of saturation that you want. You can, starting from here, move back to here. You don't have to complete a full loop. This path method here is quite robust in that way. And so the way that this works, again, is we're really just integrating this differential equation introduced by Giles and Atherton. In our implementation, we do include the ability to describe anisotropic magnetic materials. So our MAN in this differential equation actually includes contributions from isotropic behavior and anisotropic behavior. And you can use this other parameter in our dictionary, WAN, to define how strong the overall contribution of anisotropic effects is in your material. And then we just integrate this using that numerical integrator. And there are some other integrals that have to happen interior to this MAN aniso term. And we've developed a nice efficient suite of integrators, numerical integrators, for doing all of those. So It's nice and fast. It's just a simple 1D numerical integration. On the other hand, it is limited to systems that can be described by that differential equation. So it may not be the model that you want to use. Alternatively, we've implemented this Pricelock model, which again is phenomenological, smaller number of parameters. The largest, or I should say the most impactful choice of parameter here is the distribution. This distribution is going to determine how your hysterons are accounted for and how they contribute to the overall magnetization of your material in the model. And we offer a few functions here for helping you define a density distribution, uniform Gaussian and Gaussian mixture. Don't want to go into too much detail about that just yet, but you can also provide just a 2D NumPy array that directly gives the grid values. A note about that, you do need to make sure whatever the grid resolution you set up matches the size of the 2D array you provide. It won't work otherwise, so it's not like you're going to fail at that accidentally, but just keep that in mind. And we'll see a little bit farther down what grids I'm talking about here, and why this density, this choice of density function matters so much. Now I'm actually not going to run these ones live. The Pricelock model, like I said, is a good bit more expensive computationally than the Giles-Atherton model. It's I would say, maybe an order of magnitude slower, so you can see it just finished there. So minutes, not hours, but still a considerable amount while we're waiting here talking. But the outcome of this model, just doing the same thing that we did with the Giles-Atherton model, looks like this. Right away, you can probably tell it doesn't quite match the Giles-Atherton model. This is actually just a result of my still trying to find ideal parameters for this particular material, which again is a bit of a difficulty with the Pricelock model. Still something we're working on, which we'll talk about at the end of the presentation. But you can see we have the same functionality built in where we're tracing, picking points, that kind of thing. The main difference really is in the implementation. And so the way that the Pricelock model actually works is by defining these relay hysterons that I've mentioned a couple of times, where each hysteron takes on either a value of -1 or 1, and it has two parameters for each hysteron, an alpha value and a beta value, the alpha value being the switch off value, the beta value being the switch on value. And for a field less than alpha, the hysteron is off. For a field greater than beta, it's on. And for values in between, it is either off or on, depending on its most previous state. So you can kind of see how this already sounds like a hysteretics system in its own right. So we're basically just using a bunch of these with different values for alpha and beta as sort of constituent components of our material. Again, not in any physical way. These don't exactly relate to real magnetic domains in our material. It is just phenomenological, but ultimately the series of these hysterons are what's going to define our system here. And so then what we do is we just take all of the values, the ones and negative ones, which I'll call here R alpha beta for the on or off value for hysteron alpha beta, and we weigh them using this parameter mu alpha beta, and that's that weight density distribution that I was talking about that really defines how much each of these hysterons is going to contribute to your overall magnetization. And then you just perform a weighted sum over these hysterons, basically. And so a little bit of graphic help here to see what this really looks like, because this is not the most intuitive model. Here we've got our hysteron density distribution, which looks quite strange. You can imagine it might be difficult to come up with this on your own if you aren't fitting to experimental values for the curve. But we have a completely blank lower triangle, since we should never have a turn off value lower than a turn, or a turn off value lower than a turn on value. And then this middle panel here is actually the hysteron grid. So blue would be a value of -1, red would be a value of +1. And depending on what the external field is, in this case, just a field of 0, you would have more or fewer of these hysterons reporting 1s or -1s. And then when you perform the weighting, multiplying the weights by the hysteron values, you get something, a grid that looks like this, where then we would just sum over all these reds and blues to get the final magnetization of the material. As you can see here, this would, of course, be a 0 point because we have as much red as we do blue. So with all of that in mind, you might be asking yourself, well, why on earth would I ever want to use a price lock model? Seems like it's a lot of work. It doesn't make quite as much intuitive sense, and it's slower than the Giles-Atherton model. But the upside is that it is extremely robust. So pretty much any kind of uncommon dynamic, especially if you have engineered dynamics because you've done something physical to your material system, the Giles-Atherton model is quite good at capturing just about any kind of dynamics you could want to express. Here's a pretty trivial but interesting example of what I mean here. So we're free to pick just about any density that we would like. And there's no real physical interpretation of these densities. So there's not much limiting you in your choice of this density field. But as you can see, we get very interesting things like asymmetry and bimodality in the hysteresis curve here. So very, very strange dynamics. And that is ultimately the big utility of the price lock model. Okay, now let's jump right back into the slideshow. Move on. Now we're going to talk about a bit of an applied use for this type of modeling, and that is degaussing. And the concept behind degaussing is to just apply an alternating applied field in order to erase sort of whatever magnetization, or at least to confuse very heavily the history of your magnetization. The reason for this is that your recent and past states are encoded in your magnetic signature. So where you are on your hysteresis curve can tell you very much about where you've been. And as it turns out, this can actually really be a matter of life and death. Now and during World War II, there are mines that are programmed to be triggered by magnetic anomalies. They have very fine detectors on them. And nowadays, these magnetic anomaly detectors are on board aircraft even. And so basically these mines or magnetic listening stations were capable of telling which submarines came from which area most recently, and possibly even where they were first submersed. So they were able to preferentially detonate mines around submarines operated by the United States and allies. Germans were, and so ultimately they figured out this was because of these magnetic anomalies and started this whole area of technical capability, which is magnetic degaussing, which is ongoing today. There's studies using things like superconducting wires and things like that to more permanently degauss submarines and things like that. For our purposes, of course, it's also a very common experimental procedure. So if you are using a particular magnet and you want it to produce the same field this time as last time, you want to start from the same starting point and go through the same process. It may be necessary to bring it back to an unmagnetized state. So with that, let's go right into this second demo where we're going to do some simulated degaussing. And so here, we're going to do what I promised we would do earlier. We're going to first construct a simple block magnet, which is based in Radia. In this rsradia, you'll see I'm importing block and H dipole. So we've got a couple of parameterized magnet models already prepared. These are more for example purposes. These aren't really long-term important pieces of this library, but if you are interested in trying this out, they're a little bit easier than starting from your own. And so, yeah, the very first thing we'll do is we'll build this simple block magnet, just a cube of ferromagnetic material surrounded by a racetrack coil. And we'll load our hysteresis model for it. I'm just going to use the same low carbon steel model, the Giles-Atherton one that we were looking at on the previous page. And next we need to define sort of what we're going to do to this magnet. So we would like to apply a range of different magnetic fields, preferably getting it up into a saturated state, bringing it back down to its remnant state, which is what we would like to get it out of. So that's what this first big bump is saturating it and then letting it come back down to remnants. And then we're going to apply sort of this oscillating current. These are all going to be applied to the coil. And that oscillating current is going to create an oscillating magnetic field, which we hope is going to sort of jostle the magnet system down away from its remnant state. So let's run through there. You can see in this loop, this is where we're doing the simulated degaussing. All I'm doing is computing this, this current density, since that's the quantity that Radia expects. And I'm calling this magnetized function from our block magnet. applying the Giles-Atherton model that we've loaded to do the magnetization calculations, and then the J-coil to compute the fields. So that's already run. Gonna plot the results and a couple of critical points from the whole thing. So we can see we started out at this initial state, the blue circle here. We reached saturation as we intended. We decreased the field steadily until we reached a hysteretic state. And this part here is where we were oscillating the current to oscillate the applied magnetic field. And we can see we do end up indeed in a less magnetized state than we started out at, not perfect. If we do the amount of field removed divided by the original field, what I'm going to call here is our percentage degaussed, we see that we achieved about 37.9% degaussing. Not perfect, but something, depending on how important it is to get that magnetic remanence back down to zero. You may want to apply, say, faster oscillating current, higher amplitude current in the degaussing section. But then you also run into experimental difficulties, of course. It's not easy to oscillate a plus 100 to minus 100 ampere current over and over again in a relatively small, centimeter, tens of centimeter size coil. But if we were able to, this next section just runs the same simulation over and over again for various values of this degaussing current, the initial degaussing current. So it starts at 0 and it moves up to 50. And we can see at 0, you don't achieve any degaussing. Your magnetization at the end will be the same as what it was in the remnant state. But as we increase that degaussing field, we see that somewhere around 30 to 35 amperes per meter, we end up with complete degaussing. So you can, for various abilities that you have, for whatever capabilities you have as far as the current you apply, you can test them out sort of in this way or a similar way. A little bit more interesting would be to look at a more complex magnet. In this case, we have one of our magnet models that is currently implemented in the repo Radia, and it's just a pretty simple steering dipole, just an H dipole. But of course, the picture here gets a bit more complicated. We have it split up into these computational domains for computing fields, which means we also have to split up our hysteresis calculations to account for the magnetization of each of those sub-elements. This actually takes a little while, about 20 minutes to run, so I'm not going to run it live for you here. But the result is ultimately pretty similar to before. It's not quite a nice, simple hysteresis curve in this case because we're not working with one single magnetic domain. We have a bunch of these subvolumes, and this is what we're actually looking at plotted here is the average magnetization, the volume average magnetization over all of those subdomains, and then the magnetizing field, of course, because we could measure that anywhere in the magnet. This is just measured at the very center between the two poles. There's might be smarter places to pick, but the important thing is that you can see that as our field strength oscillates at the end, we do end up getting some degaussing of the H dipole. So the hysteresis models work as expected, I suppose. You see these interesting history-dependent values, and we can even see things like these oscillations in the magnetization due to oscillating field values to see something like simulated degaussing. So these models aren't, I would say, not fully complete at this point. They're implemented to a point of being useful, and so that's why we're here talking about them today. But these are just some of the ways in which you can apply them. This is a little bit of behind the scenes about how this was implemented. These magnet classes that we have, the block and the H dipole, basically just contain the constituent parameters, and they act as wrappers around the actual radia objects for now, where each of these objects is responsible for creating and applying currents and computing hysteresis quantities for the radia object. And they store all of the information about the radia object IDs and things like that. So if you do want to pull it out and use it as you would a standard radia object, you totally have that ability. We use the existing radia functionality for field calculations. We're not trying to reinvent the wheel here or anything. I did, just for the purpose of creating these classes, we did add 2 minor but useful functions. It's just sort of this recursive object container enumerator. So currently in Radia, you can see all of the objects in an object container, but each of those objects may also be itself a container. So this just returns all of its contained objects recursively. And then UT_del_stuff calls this container function, but then just deletes everything in the entire tree. So if you've ever run into the issue where you're trying to delete an object that you've defined in Radia, but you later find out that some of its constituent objects are still present, that's a nice, useful function. And then the visualizations are all done using the Radia viewer objects that are part of our Jupyter rsradia project. Okay, so to close out here, just some of the future developments we're looking at making currently. Wider selections of parameterized magnets. This is already well underway. Of course, it's part of our other efforts in providing Radia to users through repo, including other dipole configurations, modified H-dipoles that we've got parameterized, and soon we're hoping quadrupole models. We do have, as I mentioned, fully anisotropic hysteresis models, but these have not been built into those magnet objects. So either building those in or having a method for building those in will be coming soon. And then one big one that I've already started work on, of course, because you've seen the PrySoc model, is fitting parameters to each of these models. For Giles-Atherton, that's relatively simple using experimental data. There are analytical methods for doing it. For PrySoc, it's a bit harder and more computationally expensive, mostly relying on numerical optimization schemes for parameter fitting. And then the most important thing, which we're already in conversation with the original author of Radia, Oleg Chubar, is integrating these models actually directly into the Radia source code so that we're not essentially just strapping these hysteresis models onto existing magnet models, but really making our hysteresis models a part of Radia. So with that, here are just the links again to the examples that we saw today. Here is my email if you're interested in getting in contact, and links to repo and our company website. And with that, I suppose that's everything. So if anybody has questions, remember to submit them at the bottom of your screen, and we'll get to answering those now.
Awesome. Thank you so much, Morgan. That was an excellent presentation. And we do have a couple questions that we're going to start off with here. The first one up to bat is, do you have plans to add any other hysteresis models?
Yeah, so there's one sort of more modern model that's been, I think, gaining popularity called the Vinch model. And it is based on first principles, so it's a bit more complicated to implement, but it also is a little bit less reliant when you're trying to fit the model to experimental data. It's a little bit less reliant on a large amount of that experimental data. So that is one other model that we are currently deciding whether or not to go through the effort of adding that in.
Awesome. Thank you very much. And let's see, we do have another question here. Do you have anything in the future to address superconducting magnets?
Yeah, so we are currently interested in adding some superconducting magnet functionality here. The plan is to use BCS theory and to add in functionality for describing things like superconducting wires, the magnetic effects from magnets on these superconducting wires, and potentially, potentially things like allowing users to compute the needed temperatures for superconducting operation. Those are just a couple of the things we're looking at. We haven't done much work with the superconducting magnets yet, though.
Okay, great. Thanks for handling those questions. We are running a little bit long today, so we're going to go ahead and wrap it up. For all of our attendees, please feel free to contact us, support@cerepo.com, or join our Slack community. I have links for both of those in the chat. And we will send you a recording or a link to a recording of this webinar in a few days. So thanks everyone for joining us, and we'll see you in 2023. Bye, everybody.